It's my pleasure to be here. Yeah, as Lee had mentioned also, I'm actually from Edmonton, so I'm just kind of stopping by before on my way over to CVPR, and I thought this time it would be kind of fun to come over to the uni and give a talk. Yeah, and the title of my talk is Video Question Answering in the Era of LLMs. Large language models, I guess everybody here has at least heard of LLMs as the acronym, so it doesn't require too much introduction here. Yeah, so this is my group in Singapore, actually. So we work on computer vision and machine learning. It's fairly broad, I think. And the three main areas that we work on are under video understanding. Also, a chunk of the group works on digital humans. So I think that's where Lee and I also have some shared interest goals or interests, I think. And then in the machine learning side, we work specifically on regression problems for vision, which links mostly to our work on 3D pose and 3D shape estimation. And this is a picture of us some years back, I guess, in the botanical gardens in Singapore. So if any of you guys are ever out in that part of the world, feel free to drop me an email to come by and have a visit. So yes, yeah. So just before I begin today's talk, this is actually not my own work per se. This is the culmination of collaborations also, and also mostly the hard work of my two postdocs here, especially Junbing, and also in collaboration with Professor Tat-Sang Chua over at NUS. And so the bulk of the work I think that I'm going to present today in today's talk is some work in preparation that we're looking at for VideoQA with LLMs and some insights onto their model behavior. So this is work in preparation still. And then one chunk of the talk is going to be presented at CVPR this year on video grounding. And most of this is, of course, based on a data set that we had published a couple years back. So let me give you some background first on visual question and answering, which is a broader topic, I think, than what we opened the title with, which was on specifically video question answering. And the aim of visual question answering is actually to answer natural language questions about the visual contents in either images or video. So in this case of the image, right, we want to know things like if I query in natural language, what color are her eyes, or what is her mustache made of? But perhaps more relevant to today's talk is if we have this variant where we actually get a whole video of something happening. And the girl, and then you ask this question, what is this girl doing after the shaking? And then she's pointing to the man cycling. And so as the talk title suggests, we're going to focus on the second variant, which is the video. And if you don't work in this area of visual Q&A, you might think that Q&A, because we're talking about natural language inputs and we want to generate natural language outputs, you might think that this is a generation task. And this is one variant of the task as it is. This is what we call open-ended QA, and we really formulate this as a generation task. But the more common variant, which has been around for about, I guess, roughly 10 years now, at least within the vision community, it's a multiple choice setting. So this gets formulated as a classification task where I present you with this entire answer set A, and the objective is really to select the optimal choice out of these four. So similar to taking a multiple choice test, which I guess you're all familiar with. And most of the architectures and the setups that you work with for doing video QA, but also image QA as well, so visual QA in general, it follows a similar setup like this, what we see here. So you have these two encoders, one for your natural language input, so basically the question and or answer set. And the second one, which is the visual encoder for your images and or video, then you pass it into this vision language model. Maybe I should have highlighted it as black, shaded it as black would be more representative, this black box here. And whatever it churns and processes, it spits out to decode into your answer. So if I decode this now in this multi-choice setting, then it's one of the X options. Or if I really am doing true generation, it decodes it into actual natural language. And a lot of the development then in the last, let's say 5 to 10 years then has been focused on this joint box in the middle on the vision language model then. So people develop all sorts of fancy modules for adding memory. You know, how do I develop my latest transformer architecture to be able to process all of this visual data as well as the natural language data, etc. But more recently, I would say that this whole image encoder and visual encoder, because everybody's focused on this vision language model, the encoding part itself has become fairly standardized. So we use off-the-shelf models, ResNet, Clip, to encode your images. And then for the language encoder, whatever your favorite language model would be. In the older days, we might use BERT or Roberta. Maybe these are some acronyms you've heard of or not. And now, of course, large language models. And so this encoding has become fairly standard. And this funny, or let's say more interesting phenomenon that's really kind of taken over, especially with these large models and large language models, is that this language encoding has really exploded in terms of the capabilities. And so I think more representative of my diagram here then would be that this NLP encoder has fully overpowered and overtaken the visual encoder. So I think this is a slightly better system diagram, or maybe even this middle part is already a little bit too large. And so because this language encoder has become significantly more powerful, it causes some imbalance issues for our visual QA models overall. And this is what I'd like to highlight in today's talk and also motivates our study. So one thing I don't want to take away here, of course, is that the use of large language models in any sort of QA systems, I think, has been a real blessing, in that our systems have gotten really, really good. So what I'm plotting here is a curve, and you can see chronologically, I mean, it doesn't start too long ago, it starts in 2020, various video QA systems, and on the y-axis is the accuracy on a given benchmark, in this case, the benchmark of our next QA data set. And there's I think three distinct stages that I can kind of partition the progress in. We start with our baseline in 2020, which has minimal language modeling. So maybe you just have a simple RNN, which is how we used to encode words and sentences with just some embedding. Then you have this stage here where we call these small language models, if you will. I mean, this concept of small and large is always relative. Here we're grouping it into the order of about 100 to 300 million parameters in the model. Whether that's small or not, you can use your own judgment here. And then from about 2023 onwards, when large language models really took over for these video QA systems. And so examples of the small language models would be something like BERT or Roberta, and large language models then is, we can go into more detail after. And the other thing that I want to point out is really this distinct jump in performance from one grouping to the next, right? You can see from the 2020 work, the baseline from the 41% all the way up to almost 50%, right? There's a big jump. And then another 5% jump from the small to the large language models. So we're observing this significant increase in the accuracy. And so that's, in that regard, I think large language models have really achieved a lot for us in terms of improving performance. And if any of you guys working in machine learning or also vision, you know that these benchmarks, getting a 3, 4, 5% increment, usually we're dealing with 0.3, 0.5% increments, is already considered a significant achievement. Let me give you a better look at what types of questions are in these data sets that we're asking questions about. So these are two examples. Why did the boy pick up a present and then move to the sofa? And then these are your 5 options. Or why did the man in the white shirt move his lips? Is he eating something, drinking water, so on? So this gives you some sense of the types of questions we're asking. And especially for next QA, we were focused more on these, we wanted to, I think, address a bit more about video specifically, rather than just images. So we were targeting questions about causality, hence the Y at the beginning, and also specifically about the temporal sequence of events, and so on. So these kinds of things, which we think relate more naturally specifically to video rather than just images. But what we realized is that for these two examples, for instance, if you ask a large model like GPT-4 blindly, so without giving it any video information, you can get the correct answer fairly easily. And in essence, these pure language models are able to answer the questions that we have without any video input at all. So that's why I'm saying VideoQA with LLMs are great, even without the video. Another problem we realized while working on this, of course, is a bit the inverse, is if you look at state-of-the-art models and what they're able to predict, they tend to give you the same, they tend to make the same mistakes as these blind models. So in this case, for these two videos, why did the white dog walk around the pool? Why did the girl in white turn her head? I guess should be. We always make the same mistakes of these blind models, even though the correct answer is given in the visual information itself. And what this is telling us is basically that these vision language models that we're working with, they're actually ignoring the visual content. I purely rely on the language. I make some inference based on whatever priors there are stored in the language. I don't actually care about what videos you're giving me. And so this starts to motivate our overall study, where we start to dig a bit deeper into the behavior of video QA models as a whole. And also at the same time, because now there is so much development with large language models, then we want to understand what are the distinctions? How can we design better video QA models without overly relying? We want to take advantage of LLMs, but not overly rely on them, such that we actually throw out all of the visual contents as a whole. And of course, for me, because I did my PhD in computer vision also, all of this, I think, now working in vision and language, I mean, language is the hot topic that everybody is throwing into, your language plus X task here. I think maybe I'm a little bit biased. I still want to stay a little bit more rooted in the visual perception side of things and not just purely rely on large language models. So what can we do to better understand these visual QA systems, and specifically for video, so video QA? So if you recall, we showed this progression of the various models and how well they did, and we had these two distinct stages of the small versus the large. What we did was we picked out a selection of them, a selection of these LLM-based models, as well as some of the top-performing small models. So this is our selection that we're doing a battery of experiments on. And they have a fairly diverse set of language models as well as the visual encoders. What we consider as large, we have this variety here, starting with Alberta, which is about 1 billion parameters, all the way up to Vicuna, 13 billion parameters. And then for the smaller models, so these large language models, we use frozen, right? So frozen as off-the-shelf encoders for the natural language inputs. And then for the small models like BERT and Roberta, we still have the capability, then we fine-tune them on the training set as well. And so the smaller models are about 120 or so million parameters, and so it's about an order of magnitude less. And our main test beds are, of course, our own, we're motivated to work on our own data set, this next QA for video, which is mostly multiple choice. And then we also experiment mostly with this MSVD QA, which is an open-ended, so generation task type of data set as well. And then we throw in these other two for specialized tasks, but I'm not going to cover these today. So this is roughly our setup. And what are we actually comparing between these large versus not large models, and what types of behaviors are we probing? This kind of brings me a bit to the outline of what I want to cover in today's talk then, is where I want to provide a comprehensive analysis of MLLM behavior. And from here on out, I'm going to use this acronym MLLM, which is actually short for multimodal LLMs, if you will, to refer to the vision language model, which features an LLM encoding. And I want to run through these 4 pillars, so time pending. we can try to cover all four. Starting with temporal understanding, basically we want to ask, are these models able to distinguish events that are happening before versus after or concurrently? We want to look at visual grounding to know whether these predictions are actually anchored on relevant content, visual content or not especially. We're looking at multimodal reasoning. So we're asking, is the reasoning for answering this question, is it based on both language and visual input, or is it only one or the other modality? And finally, examine things from the perspective of robustness. So if we make perturbations on the inputs, whether it's the visual inputs or the language inputs, video in question, I guess, should also be answer. If we make perturbations on these, what happens? In terms of the analysis, the way that we go after this is by specifically modifying the question or answer or video input set, as well as the architecture, to compare the before and after performance differences. So in that regard, I think this analysis is not terribly mind-blowing in that sense. It's more about these specific aspects that we really make these specific probes that give us some insight. So let's jump into this first one on the temporal understanding then. The question we're asking really is, can multimodal LLMs distinguish temporal relationships between events? So you see there's this video here of, I think it's a guinea pig or some sort of pet. And the question is, what did the person do after she took the black item away? And the correct answer is she patted it, or she's stroking the animal a bit. The reason why we actually care a lot about these temporal relationships, I think it's rooted a bit in this distinction between working on video versus images. We want to treat video as more than just a bag or collection of images, collection of frames. And so we really focus on questions that force, I think, some kind of reasoning about the temporal relationships, about what's happening before versus after in the video itself. And so if we look at this question then, what we did, we focus on these signal words about time, like before or after or when, during, etc. And what we would do is then look at the events that are this relationship is anchored on. So the event is, after she took the black item away, this event. And we adjust these questions. We edit these questions based on these relationships, right? So she takes the black item away, then she pats the animal. So now I can switch up the question, right? Before she pats the animal, she takes the black item away. So for any human in parsing these sentences, these relationships are equivalent, right? Is that also the same case then for our VideoQA model? Another type of edit or change that we do is just purely change it into a descriptive task, right? So almost a bit like captioning, basically, what did the person do? And then these are 5 choices, so these are a little bit more confusing, 5 different options based on these 2 events and this temporal relationship in between. Is the vision language model able to discern what the actual true relationship is? And so the way that we're going to analyze this then is basically compare the performance of various models before we make the change. So this is what I'm showing in performance on the gray bars here. So on the y-axis is purely accuracy in this multiple choice. And of the 5 that I've listed here, the one on the left, this co-VGT, is the small model, and then the other 4 are LLM-based models. And we're going to compare then with the performance after we make these edits for the same questions. And what you can see here, of course, is that there's some drop for both this temporal exchange test, where we swap the events, and also this description test. And then we also look at something called the flip rate, which is basically how much of the answers change. So maybe I got it wrong the first time. If I get it wrong the second time, then I can't tell any difference. But we just check basically, did you change your answer at all? How much is the answer affected, regardless of whether it's right or wrong. And so this is the way we do our analysis in that sense. And our findings, based on this type of temporal relationship probe, is that 1, these models are not very consistent, unfortunately. So there's a fairly high flip rate, ranging from somewhere between 50% to about 75%, right? After we make these adjustments For the most part, the models using LLMs tend to do better than our baseline, which with the small model. So this we can tell by looking at the original performance. So our original small model is about 5% lower, 5 to 6% lower than our LLM-based model. And in general, they tend to do better at these temporal exchange events. But it's not totally clear why they're able to do so right now. We think this is likely due to some language priors or some common sense knowledge of the options. But this is also intertwined, I think, with some other effects, which I will cover later on. And then the most disappointing result, of course, comes from this. If you look at the second graph, which is this temporal description test, we just asked, what happens in the video, or what did the girl do? And then they had to distinguish between the 5. The MLLMs tend to do much poorer, especially you look at the drop between this one model here, right? This video chat 2. It dropped very drastically, right? In terms of distinguishing the content ordering. So our takeaway from here then is that MLLMs tend to struggle with identifying temporal relationships. And to some extent, this is not so surprising. If you work in video or action recognition at all, it's fairly well established that actually video models tend to rely very little on the motion information and temporal ordering in the data. Not that they don't care at all, but what motion and time ordering adds to these models is incremental compared to the actual visual contents. So they don't care too much about the motion and time, and there's a fairly strong static bias towards the visual contents in terms of the objects or the scene, which you can distill from a still frame. And of course, this effect then tends to carry over also to video language models or vision language models as a whole. We can try to mitigate this. There's been some work on this by improving the whole learning scheme, by adjusting some contrastive learning types of learning schemes that are more time aware, or doing some dedicated data synthesis or data augmentation to really force the model to pay attention to these differences. So there's been some works on this. Other promising directions that we think we're looking into at the moment is more about this explicit modular reasoning. Basically, you set up a special dedicated module to say, you basically prompt the language model specifically what happens before versus what happens after, and then is this consistent with the what happens after versus what happens before, these kinds of things. And so these are avenues that we are looking into for improving this temporal relationship understanding. Okay, so now I want to move on to the second part, which is on visual grounding, to check if the predictions are anchored on relevant video content. And so this portion is actually what we're going to present at CVPR next week. What do we mean by grounding predictions on relevant content? The idea behind it is, let's say I have some video. This is actually the example that we opened with. Why did the boy pick up a present from the group of them and move to the sofa? We feed them into our VideoQA model, and we get this answer to unwrap it. As we said, actually, this is multiple choice, so it's selecting this from 5 different options or so. And what we want to do, or what we're hoping to achieve, of course, is to substantiate this answer with the relevant visual segment. So it's a temporal isolation or temporal grounding of where this answer occurs in the video itself. And the standard way of studying grounding is to analyze, so usually these vision language models, they have some sort of attention scheme embedded inside right now. I think transformers are fairly standard use, so we just examine the attention scheme and look at which portions have higher attention scores. And so that's what we're using as our naive baseline in a way. And then we also introduce another reasonably naive approach, which is Gaussian masking, basically to isolate the parts of the input which are relevant. And so based on the input question in the video, we have this grounding framework to estimate the relevant segment, what the relevant segment is, before we answer the question. Right. And so these are these two naive methods of assessing grounding. And to get a sense of how grounded the current models are, what we're going to do is basically compare the accuracy. On the x-axis, we're purely comparing the percentage of percentage of questions which get answered correctly. And then on the y-axis is where the question is both answered correctly and based on whatever scheme that we're using for grounding here, looking at, was it able to predict the correct visual segment for which this answer is based? And so if everything is perfectly grounded, then what we should have is something along the identity line here, right? And if we consider human performance, we're pretty good at answering questions. We're not fully grounded, but almost. If we look at actual state-of-the-art performance, this is where we're sitting right now. So we're not as good as humans at answering questions. I mean, that's okay. But what is, of course, more concerning is this big gap here in terms of the grounding, right? Of what we're able to answer as questions but cannot substantiate with evidence. So where does this gap come from? So we checked for two things. The first is that we check for natural language shortcuts by looking at the blind QA results. So this blind QA is like the example I showed earlier, where we, instead of this whole framework where we have both the question and the video and the answers, we basically removed all the visual inputs, right? So in this case, it's the video. We fully removed that. And then we forced the model to answer the question still. And unsurprisingly, from what I already opened the talk with, we managed to answer almost 80% of the questions that we got originally. So this is really telling us that there's a lot of language correlations between the question and answer set that drives the overall performance. Right. The second types of reasons that we looked at is to say, well, we think there might be some spurious visual correlations. What we mean by this is basically we get some information from the visual data, but it's not the visual data that we're actually expecting for the actual answer. And the way that we check this is with some oracle setups. One oracle is to exclude the answer, right? So if I don't actually give you the answer portion, but I still give you some other parts of the video, how well do you do? And then there's only a 1 to 2% drop in the QA performance. If I give you only the answer, this is the correct portion, it's already pre-grounded for you, my gains are actually less than 1%. Right? So minimal gains for giving you the answer, minimal drop for not giving you the answer portion. But I mean, there's still this distinction in the sense that you can say that, giving some kind of visual information gives you this extra 10 to 15%, right? Because in the blind case, we're achieving still 10 to 15% lower than the non-blind case. So there's something in the visual data that helps us answer these questions. But what this something is, we're not sure what it is, and it's definitely not this actual answer portion, right? So that's why we call this spurious visual correlation. So visual inputs support the QA, but only spuriously and is independent from the grounding itself. Our takeaway from the visual grounding study is that the really great performances of these MLLMs, they're poorly supported by the visual evidence, and it's likely that a lot of this performance then comes from the very shortcuts and spurious visual correlations. And to improve grounding, we need to take explicit measures. There's been several works in the past already that have looked at this problem both in images and now also in video as well. A lot of these approaches, including what we've done ourselves also, is to take some learning-based measure to instill the sense of time grounding, temporal grounding here, whether it's pre-training on aligned sentences or giving special attention schemes, contrastive learning, etc. There's all these other schemes. And one direction we've started looking into, which is a bit more interesting, is basically, can I relate specific chunks of video to specific chunks of text, so this captioning, and then ask the LLM to do the actual reasoning. So basically we pre-ground before we make any reasoning or ask any questions, and then that way it's already isolated, at least in a segment basis. So let me move on now to this third topic on multimodal reasoning. In this case, we want to check how much of the reasoning is based on both language and visual inputs, and not dominantly focus on one or the other. I mean, the assumption here, of course, with everything that I've led up to, is that we do almost all of our reasoning based on the language and not so much on the vision. So how do we, so does it actually do sufficient reasoning based on both the language and the visual inputs? And one thing which we looked for were correlations between the answers in the video. So, and also correlations between the answers in the question itself. And what I mean by this is that for the first case, for instance, if you have correlations between the video and the answers themselves, so this is the same example again with this pet hamster or guinea pig. One issue is that the correct answer itself, this animal, is the only thing that's linked to the video itself, right? Of all the other 4 answers, they have nothing to do with the video, right? So as long as I can recognize that in this video there's some kind of animal, likely this is the correct answer. So this allows me to fully ignore the question, right? I don't care what the question is. Likely the answer has something to do with animals because the video is about animals. Similarly, in this question to answer correlation, yes?
Sorry, just curious about the setup, but it's a Q&A problem, right? So the multiple choice question setup, would that be some kind of source of bias?
Yes.
I say, expect more toward video or just toward the language model.
Yes, that also. By virtue of providing this answer set, you've already somehow pre-biased what your model is able to interpret. Hopefully with the open-ended question setup, it makes things a little bit better. And that is one of the trends or patterns that we see actually is you might see one trend with this multiple choice type of data set and setup, but you observe the opposite in the open-ended. And that's we observe similar. So I think in the next one I jump to, or maybe the ones after I can show, we do observe these results. So yeah, exactly right. That's a very good point there. Any other questions before? Okay. The second type of correlation is basically your answers themselves are not related to anything having to do with the question. What do we mean by this? So this is a slightly different question, but related to the same video. What did the person do after the animal started sniffing the black item on the bed? And if you look at all the 4 answers, basically remove the black item is the only one that has any sort of match to the question itself, because this black item is the common link here, right? And so if I purely rely on this, then I can ignore what actually happened in the video because I just have to search for the common keywords and so on. And so one way to fix this, what we did was we run an object detector and also recognition on the video itself to extract the objects and also actions, and also find similar keywords as nouns and verbs in the questions themselves. And then we edit the answer set such that we basically make it more difficult with these more distractor types of objects, right? Both in the answer set for the visual answer, the video answer correlations, and also the question answer correlations. And again, then we compare, what is the drop in performance after we make these edits, right? Essentially, we've made these harder. The answer is much harder, right? In a way, you can also think of this, if some of you guys are teaching assistants or you've ever set questions for exams, this is a similar process that we also go through, right? How do I make this question a little bit harder for the students, right? You want to put in much more difficult distractor answers, if you will, and that's the essence here of what we're doing. If we look at the performance, you can see again basically that actually the drop so overall as a baseline, so the leftmost bar is our small model, and then the 4 right bars are our large language model performances. They're better than our small model overall, right? But the drop sometimes actually is even larger than the small model itself. And also the flip rates tend to be higher. And what's more concerning also is that some of these large language models actually drop below, like this one here, and this video chat one also. They drop below our small model, right? Even though our small language model is an order of magnitude less than these LLM models, right? So what we're concluding from these results is basically that our current video QA models largely rely on these correlations to answer the questions. There's quite a bit of accuracy decrease in flip rate, and some of these large models actually do worse than the smaller models. Yes?
Are these performances for retraining or just on sheet?
They are not retrained because all we did was change the answer set, right? Yeah.
Nice.
So this phenomenon that we're looking at here of these correlations, you could argue that this is a problem in the way that the data sets are set up, right? If we didn't set them up well in the first place, such that the question and answers themselves are, there's data set bias, right? You set up these data sets poorly such that it allows these correlations to come through. And in that regard, I think data set bias for visual QA, this is fairly well studied. It occurs also in images and also in videos. This has been studied in several works. And so people try to then come up with different methods to prevent your visual QA models from being too biased based on the training data, for one. Also, things that you can do to basically check when you're curating the data set in the first place. How do I prevent it from being biased, et cetera, right? Where do the biases come from? From the language itself, maybe, from the annotator, also from the curation bias, and also from out-of-distribution concepts. So to give you some sense of this is, maybe men wear glasses more than women. This is a nice example, actually. I think whenever they ask you to do counting, I mean, in our data set, we don't do counting, but some of these older image data sets, they always ask, how many bananas are in the photo? How many sheep are in the photo? And the answer is almost always 2. Like 2 seems to be so this is let's say curation / annotator bias in a way when we select these things, because we tend to like somewhere in the range of this. So all sorts of biases that exist. And one that's kind of interesting is also this idea of out-of-distribution concepts or rare concepts. So, how often is it that you see a child sitting in the fridge, right? Even though that's what the image is. The child just, where is somebody sitting? The most natural answer, based on our language bias, also our common sense, is somebody sitting on a chair. Right? They're not sitting in the fridge or on a tree. One curious thing that came out of this is actually, with the introduction of large language models, what constitutes out of distribution or rare? So there was this version of our next QA data set, which is the next OOD setting, where they basically tried to rebalance the answer set for all of the objects and actions such that you have a much more even distribution. You don't have this long tail distribution with these many tail objects that you would probably not cover, or tail actions. And surprisingly, our MLLM models, they tend to surpass the previous state of the art that are not large language models by a significant chunk on this rebalanced out of distribution data set. So what this is telling us is essentially, and also then the drop between the original, let's say, non-balanced data set here in, where is my laser is a little bit dead. In this next QA versus the balance, the drop for these large language model, LLM models, is minimal, which is kind of telling us that actually, because these models are so big, what's considered out of distribution or what's considered rare is maybe not as rare or out of distribution as we used to think it is, right? Just because of the sheer amount of training data that goes into learning these models. Okay. I have about 3 minutes left, so I think I'm going to jump over this last topic and jump straight to the very end result. For this last one on robustness, our objective was basically to do a bunch of probes where we poison the data and attack the data by doing all sorts of things. One is adding spoken phrases and rephrasing the questions. I think this is fairly easy to understand. Let me try to get my mouse back so I can jump things a little bit quickly. Another was to shuffle the video frames and the question words, remove a bunch of keywords. And the expectation here, of course, is that if I fully attack my data, I give you nonsense video where all the frames are shuffled. I give you nonsense questions that don't make any sense here. Or I even remove some keywords. I remove the nouns. I remove the question words. You have no idea what it is I'm asking. The expectation, of course, is that you should have a significant performance drop. Do we get this performance drop? And I guess the whole theme of the talk leads to the not so surprising conclusion that maybe we don't get as much drop as we hope to have. So I'll jump straight to the conclusion of this point here. Basically, ideally, we should be robust to reasonable perturbations, right? Just by rephrasing the question a little bit, right? Adding some spoken phrases and so on at the beginning of the questions. And we should be sensitive to the data poisoning. We're somewhat robust, somewhat brittle. We are somewhat robust to the perturbations in the questions, but we are not as insensitive. We are not as sensitive to the data poisoning attacks as we would like to be, especially on the visual frames. You can fully shuffle the visual frames out of order, so it's a nonsense video, but you still get the same performance, right? And of course, this kind of links to the challenges that we have in visual grounding in the first place, right? All of these phenomena are somehow linked in that sense. And similar to this perturbations in the questions, if we're not robust to it, it's because we're really relying on these correlations and so on. We haven't actually fully understood what is being asked in these questions, right? And because of this insensitivity to the poisoning attacks, it leads to questions for us, right? Is this model explainable? Is it trustworthy, right? Because actually what it's doing in the end is still too black box to understand and interpret. And of course then leads us naturally to these questions of how can we link to these concepts of causality? Well, we're asking it to give you concepts of causality. We're even asking the model itself to explain, why did you make this choice? Why did you make this decision? But based on all of these probes that we've done, actually, it seems maybe it's just spitting out nonsense for us still. One promising direction that we are looking into also is to add this chain of thought. So this chain of thought procedure from NLP is basically to ask from multiple steps of reasoning to arrive at the answer, to improve reasoning and grounding as a whole. So in terms of conclusion and outlook, I think what we've established is that MLLMs, so visual QA models, or vision language models as a whole, which feature LLMs, they excel at this task of video QA. They're really good at correlating contextual cues and generating accurate responses to a whole lot of questions. And they're getting better and better by the day. But the superiority, let's say, of these models, which feature LLMs over just our standard language models, is not so clear-cut, or not as clear-cut as we would like it to be. Even though we think, wow, when you use ChatGPT every day, it's phenomenal, right? What it seems to be able to understand. And one thing that we think that they're better at is maybe exploiting these various biases that are present in the data sets. There seems to be, at the moment, a heavy reliance on the language modality and very limited use of the visual content. Some of it has to do with the fact that our visual encoders, like CLIP and so on, our large vision models, they just haven't caught up yet in terms of the progress that we've managed to make for language models. But we're still missing several of these desirable properties that we hope to have, whether it's groundedness, robustness, or being able to discern temporal relationships. And so we really need to take steps and measures to try to instill more of this when we're developing and training the models. And so in order to make progress in this area, I think we need to really balance our aims with accuracy, which is the sheer black box training approach, right? I just try to improve the overall performance with these additional criteria to improve robustness and explainability and so on. Yeah, and with that, I'm happy to take questions.
So to some degree, you could steer a visual language model's dependence on the visual language component, right?
Yes.
Would steering it more towards the video help, or do they already have an optimal balance?
So I think the challenge is knowing how to steer it in a way that is effective, I think. And this is what we struggle with at the moment. I think all of these techniques that try to improve it basically based on this explicit modular reasoning, you ask it to ground it on the data, you end up with usually a fairly large drop in performance then also, right? And at the end of the day, and I think this is also partly rooted in our publication culture, is everybody's pushing for numbers on these benchmarks also.
That's right. So there are very few studies like yours compared to ones that extol the virtues of the next new thing.
I think that's not totally true. I think there are several works that have slowly started into this trend of basically it's not just purely about system development, how can I push this number higher, but also about explainability and understandability and analysis of what is actually happening. So I don't want to claim that we're the only ones doing this by any means, yeah. And I hope that it picks up more also to really understand what's happening.